Well, good evening. Thanks for your interest in practical amateur radio measurements, courtesy of Bob Whitty and K0NR. I'll be presenting tonight. I'm Jonathan, AE0WO, along with Hans, W0PU. And we'll be talking about several instruments that are used to measure voltages and frequencies inside the radio spectrum that interests ham radio. So how we're going to do this, we're going to talk for about 20 minutes in general. Then we're going to go into specifics about multimeters. And finally, when we're done, we'll give you a chance to touch some of the multimeters that are here in the room, maybe do some experiments and tests over there. So why do we need electronic measurements? Well, Bob's first law, that's Bob Whitty, of electronic measurement. With electricity, most of the time, we can't observe what's going on without actually measuring it. There's no observable visual of electricity. And Bob's second law says, when you can observe electricity, it's often a bad thing. You're getting zapped. So to measure is to know. And if you cannot measure it, you cannot improve it. That's what Lord Kelvin said. Bob's third law. Lord Kelvin was right. So what are we measuring? We're measuring things in the electromagnetic spectrum, all the way from DC up to gamma rays, possible to be measured. But what interests ham radio? Just the section that's circled in yellow. Really everything DC, like power supplies, voltages in your wall, computer systems, radio waves, right up through microwave. So what are these things and what kind of tools do you use to measure them? So there's DC, AC power, audio. Well, those are typically can be measured with something like a digital multimeter, which we're talking about tonight. If you're talking about higher frequency, that is the LF, MF, HF, our favorite, and VHF and UHF all the way up to microwave, you would typically be using something like an SWR or power meter. You're not measuring the item itself, but the power of it, or an antenna analyzer. Something like that would be a tool. But tonight we're going to talk about digital multimeters. There's oscilloscopes, there's signal generators, there's RF communications testers, lots of different equipment that can measure these signals. So let's talk about some terminology. When you talk about accuracy, it's the closeness of the agreement of the measurement to the actual value. So if there's a calibrated value and your meter reads very close to that, then it's accurate. There's uncertainty in measurement, quantified by the amount of doubt you have about the results. That has to do with sampling and lots of statistics. We won't get into that much here. There's repeatability. When you put the instrument on under the same conditions and you get the same results and they're very close, then your instrument is very repeatable. It may not be accurate, but it's always giving you the same number every time you measure it. And the neat thing is so smallest difference that can be meaningful to distinguish is resolution, the change in like the ones digit. You'll see that multimeters have a range of digits. Look for the last digit. That's your resolution. The trends that we've seen in measurement equipment, they're getting to be very low cost. I mean, some of the machines used to cost $40,000 are now $40. These kind of ranges. They're PC-based instruments. You don't even have to have much of an instrument. You plug it into your PC, and your PC does all of the calculations and visual displays. There's even software-defined instruments. You take a very raw signal into the computer, and it does all the analysis for you and graphs it. There are some low-cost instruments. Typically, they're coming from China. They're usually lower quality, but they might be good enough for what we're doing. So keep that in mind. There's even some very disruptive technologies, like I mentioned. I think Jim had told us one point that these analyzers just cost $40,000, and they came in a big box, and now you've got the new Nano VNA. It's very disruptive, $40 or $50. Does the same thing. Disruptive technology, yeah. Then there's PC-based instruments. These come in a very small device, and it's connected to your USB, and it uses the PC as a power display and also lots of computation and lots of multiple functions. You can add on additional software to do further analysis. And with that, I think I'm going to turn it over to Hans. Hans is going to take us through the first part of digital multimeters.
I'll try. So here we come to a bit of the meat of the day. So a voltmeter, yes, that's what it is. An ammeter, that's what it is. And then they combine all of that in one instrument. And that's now a digital multimeter. It measures DC and AC, usually. And there's models that do a lot more, like diode testing, continuity testing. That means does the signal that goes in come out the other side. Capacitance, inductance, frequency, temperature, and even some do transistor measuring. It can be a bench or a handheld form factor. If you look at the front there, the one standing up, that's a bench meter, and then all the other ones are handheld form factors. Most are digital meters, and there's still a few analog meters. You'll see a picture of that. It began a long time ago. In the 1700s, they found out that if you put a stick to that bottle with a gold things in it, then they would split, and if you took the electricity away, they came together again. Not very useful anymore, but it was found out a long time ago. Then we come very close to what we're using now, an AVO meter, amps, volts, and ohms. You can build one yourself. The schematic is right there, so easy. And this was in the early 1900s, a usable multimeter. This is one of those analog meters, and it looks very similar to a digital multimeter, except there's a needle that tells you what the measurement is.
The best damn meter ever made, right there.
The Simpson, yeah. Photo by Bob Whitty. Yeah. So there's tons of them around. The top one on the left is a Fluke. It has all the yellow on it, yellow jacket. They're expensive. And then there's a bunch of others. Auto ranging, meaning it looks at how much power or how much current is going through it, and it automatically adjusts to that level. There's ones where you have to guess what level you're going through, and yeah. And there's that's the one, the yellow one at the bottom. You want more? Let's try that out. Yeah. So, what can you do? You got a power supply. You want to know if it actually outputs what power it's advertised in the manual. See if your HT battery pack is fully charged. Measure the current that your transceiver draws. Then you can find out how long it will last when the main power goes out. You got a bunch of resistors. You can test them. A fuse. It's usually good to see if the fuse is blown, because otherwise you may have a problem somewhere down the road when you're measuring amps with a multimeter. That's getting a bit more difficult. Then there is one that I don't understand, but Jonathan will. Bias voltages against the service manual, if you can find a service manual for your machine. So figure out if the AA batteries are working. I have several batteries over there. Some are good, some are not. Is your coax shorted between the shield and the sender conductor? Something you can easily measure. Is the power line voltage in your shack okay? Should be around 120 plus or minus 6. And check for the continuity between the ends of that cable you just soldered. And that's usually done best before you actually apply it in something. So it is electricity, and the more voltage there is and the more amps there are, the more difficult it gets to work with it. Yeah. Yes. So, yeah, you should have one. You should have one.
For the
Even that, yeah, but with one you can make do. The digital, of course, the analog ones are now kind of in the past. There is a rating for these things, and that is the minimum rating you should get that will keep you reasonably safe using normal voltages, etc., that you have in the house. Well, DC voltage, AC voltage, resistance, and DC current. Yes, good. AC current, not necessary. And if you have it, then you need to take some, be a little more careful. So, and we mentioned continuity test, the diode test, auto range. Auto range is very handy because it will adjust to the power or level that you are measuring. Some of them have an analog bar graph. That's just a dash that runs through the display to the level of maximum to minimum. Battery test and the true RMS. That's something you all learned about in all those tests you took. Here's one that's on the screen and is also on the table. Simple, but it does measure just about everything. And they're not expensive. General overview of what's inside these things. Batteries, an IC that does the actual measurements, a beeper for continuity and some other measurements, and protection fuses, important. And here we come to a slide that you memorize, of course, and then you can build one at home. But I think I'm going to hand over to Jonathan for the technical part.
Thanks a lot, Hans.
Oh, yeah.
So yeah, there's a lot of some additional components, but mainly it's driven by the one chip. So there's basically it's voltmeter on a chip, and a lot of little extras for testing transistors and other components. So it's kind of nice that they did that diagram for us. So long ago, this George Simon Ohm, 1700s, early 1800s, he said, "Messen ist Wissen." What does that mean? Measurement is knowledge. Ohm noted that the current through many devices was proportional to the applied voltage, and so he came up with Ohm's law, which you often see written as V equals IR, voltage equals current times resistance. Or you can solve it for current or solve it for resistance, listed here. In a simple circuit with a battery and a resistor, we have here the voltage provided by the battery, labeled as E, probably as electromotive force, right? Not voltage, but E. It produces a current, and the current is flowing through the resistor. And the current that flows is E divided by R. So how would you measure that? Well, you can get out your voltmeter and turn it onto the voltage scale. And initially, the multimeter would appear as open circuit. Then when you connect it, the leads across that resistor, that's where the voltage drop is occurring. You measure that in parallel. So you'll get the reading of the voltage drop across that resistor. When you're measuring current, you do something a little different. You break the circuit. So you connect the circuit through your voltmeter. So all of the current is going through your voltmeter. Your voltmeter is acting almost like a wire. Be very careful when you do this, because if you don't have any resistance, essentially, like you've hooked the amp meter directly to the battery, all the current will try to flow because there's almost no resistance. And you'll probably blow that fuse. Yeah, before it wrecks your meter. So be careful how you're connecting when you're doing current mode. And any short circuit can cause a real problem in your device. Be careful. When you're doing a resistance measurement, you have to pull the resistor out of the circuit. You can't measure it while it's got power going through it, because the meter is providing the power. The meter is providing a small voltage across that resistor and measuring the current that's going through. That's how it knows what that resistance is, using Ohm's law. So make sure there's nothing else in parallel with the resistor. Sometimes very difficult if you're testing in circuit. What you'll get is the resistance of all of the components between those 2 points. So a whole mix of things. You might have to pull the resistor out to get the true resistance of that. And the principles apply to diode and capacitance, inductance, and continuity. You have to pull it out of circuit. So let's experiment. Can you talk to this one?
So you can see there's the multimeter. It shows about 120 volts, 118.8. And you see that, I think it's a male hand there, that puts the leads into the socket. And you can see the red one is in the right hand, the smaller little hole, and the black one is in the bigger little hole in the socket. And that's the positive and the negative. Now you see that he does that with one hand. Why does he do that? If you put him in with two hands, then the current goes through your arm. If something goes wrong, through your heart, out the other arm. The arms don't mind that much, but the heart might. So that's kind of important to present. There's other ways of measuring current in the socket too. You may have tried that. 120 volts, yes. That's the way you tried it when you were young, right? Yeah. And you all survived because you were lucky. Or you put it in the big hole, which didn't do much. Ah, yes. And how did that feel? Yeah, yeah, yeah. No. Yeah. Okay. Now you want to measure the current that goes through the wire in your house, between the socket and some machine that you're using. Then you have a clamp meter. The clamp meter, it opens when you hold it, and then it closes, and it will measure what goes through the wire. Oh, but there's a problem. There's the positive and the negative both go through the same wire. And so the result will be 0. Therefore, they have found out that if you put one of these in between, then you can put the clamp on that, either the top hole or the bottom hole, and it splits the black and the white wires in two, and so you're only measuring one wire now. And the two little holes at the bottom, you can put your leads into it to measure the voltage. So both the current and the voltage can be easily measured that way. Samples are over there. Oops, this looks technical.
Thanks, Hans. All right, I'll take it. Yeah.
Yeah. Oh, yeah, yeah.
So here we have a simple sine wave voltage. And if you remember from your amateur extra studies, you know, the VRMS is 0.707 times the VP, so the single peak. Or 1.414 of the RMS voltage. We all remember this, right? So let's talk about what is this? What is it? Peak to peak voltage. So that's the highest peak to the lowest peak. The VP is just half of it. So from the baseline up. So from 0 voltage to the highest point. AC voltage is going plus and minus all the time. So what is RMS? Well, it's this 71% of it. Why is that important? RMS voltage. Well, it kind of follows Ohm's law. VRMS equals I over R. So here, let's look at an example of AC line voltage. So the line voltage in your house, you've heard of it, is 120 volts, pretty common. That's the RMS voltage. So what's the real voltage in this? Well, the peak, single peak is 170 volts. Peak to peak is 340 volts. So that's what you're feeling when you touch those two wires like this. 340 volts, back and forth, not 120. Let's talk about accuracy and resolution. So you've seen several, you're going to see on some of these multimeters later that they have like a certain number of counts. So 2000 count is when the first digit is a 1 or a 2. I think one of your meters was a 6000 count, so you have a lot more digits on the first point. And if you're measuring, for example, a 13.8 volt power supply with a 312 digit, the actual value, let's say, is 13.8385 volts. And the measured value on your meter, like a pretty good meter, comes out 13.84, but that's all it can measure. It can only measure to that last digit of 4. So the resolution on this meter is 0.01. So in this case, the accuracy is, versus the real one, is 0.138 volts. That's the best it can do. And our measured value of 13.84 has an uncertainty as well, because 0.138, the actual value could be actually between 13.702 volts or 13.978. You don't know because of the resolution on the equipment. But keep in mind that the resolution is usually actually better than the accuracy. So it's got a lot of digits there, but there's a lot less certainty of where the actual value is. But relative measurements are very good. So if you're measuring a voltage that's slightly up from that, you know that that amount of voltage in the range of the meter is pretty close. So it's much better than the accuracy, yeah. So a man with 1 clock knows what time it is, and a man with 2 clocks is never sure. Why don't you measure the same battery over there with multiple digital multimeters and compare the results? Which one is right? We don't know. You have to have a calibrated equipment to find out. You want to take it, Hans, or you want me to finish it off? Okay. Yeah, that's what we're going to do.
I'll go through a few of those things over
All right.
there.
Why don't you point the camera over that way? Let Hans talk through each of the meters we have.
At least the ones I know, and then you can do yours. Yeah. Okay, we go through history a little bit. This is a multimeter made by Fluke in 1979, I believe, and it still has mechanical switches here to choose the various ranges that you wish to measure. But it measures everything that the basic multimeter should measure. And it still works fine, calibrated, more or less good. Interesting story about this one. It is the first really successful digital multimeter that Fluke made, and the engineer that designed it was asked to do a presentation for IBM at the headquarters, and he was joined by a salesperson from the local area. The presentation was given by the engineer, and the salesmen just sat there, and they thought they'd sell maybe 1,000 or so to IBM. And a few weeks later, IBM said, "Yeah, we'll take 10,000." And of course, the reward went to the salesperson. Yeah. Okay, in 84, this was followed up by this machine, and it looks very much like a current, one of the current meters with the. Yeah. Oh, okay. And it looks very much like more recent meters. This also works. 1984. It was designed for the American government, and they also sold a heck of a lot of them. This looks like a modern Fluke multimeter with many functions, including at the top, you can hold it to the wall and it'll tell you if there's any electrical current flowing through wires there. An extra little function. This is the one that I showed. It's the Astro AI 6000. About 30, 35 maybe dollars at Amazon, and it has just about everything you can want in a multimeter. So far, it's worked. Clamp meter, also a cheap one, and that meter that I showed for the splitter. And one of us had a very, very small multimeter that you can put in your pocket. This is a little board on which you can test your multimeter to see if it measures exactly what this thing is calibrated for, ohms and volts. And I have some batteries that you can test for yourself. Some are good, some are not. There's a board here that you can test to see if there's volts and how many, and the resistance that the circuit has. And I think Jonathan has a few of those too. Here you go.
Okay, so thanks, Hans. So what I have is also another clamp meter. This is an old one, 1980. Still works. Manually select the range that you're going to work on for this little spinner thing. Pretty fancy. Things have come a long way. I did work at Radio Shack in 1982, and I bought this top of the line bench digital multimeter. This was really fancy for the time. It does everything. It even measures the gain on transistors, which you can do right here with these little clips. And what I got here is some examples. I've got series resistors, so you can see that resistance in series adds. And I've got resistors in parallel, so you can see that resistors in parallel are 1 over R equals 1 over R plus 1 over R. In this case, it cuts by half. And I've even got one with corroded electrodes, so you can see what happens when you're trying to read something that's not clean. Okay, does the resistance show the right number? I also have an NPN and a PNP transistor, so you can check the gain on those. And I've got the spec sheets for them right here. You can find out if one of those components is defective. Here's a hint, one of them is. See if you can find out which one. So that one cost a fortune. I don't know, like half my salary for the month or something. It was some crazy number in 1982. So what happens in 2015, 2016? You go to Harbor Freight and you buy a screwdriver and they give you this for free. It does everything that thing does for free. So, and I have a couple of batteries too. But anyway, I think we'll go into the practical part if you guys want to come up and experiment. Which one is right? I'll let an electrical engineer do that. Any volunteers? Chemical engineers are no good at this.
So I would maintain that if you take two of those meters and measure the same thing, they're both going to be wrong as far as accuracy goes. So can anyone tell me if they have an idea of how they could tell which one might be more correct than another? And you have to know something else about the meter to do it. When you put a circuit you put the voltmeter on that circuit, that resistor, you're actually putting another resistor in parallel with the resistor and voltage that you're trying to remember or trying to measure. So the answer would be, if you don't know what the input impedance is on the voltmeter, you can't tell which one's going to be more accurate. They're both reading accurately. It's just not what the real voltage is because of the impedance variation on that on the equipment. So just a nuance. If you're trying to make measurements in a very high impedance circuit, it can cause you some problems, because if you have 100,000 ohm input resistance on an amplifier and you've got a multimeter that's got a 10,000 ohm input impedance, you're going to be way off with that, because you've lowered the input impedance of that device that you're trying to measure by tenfold. So you have to be aware of the type of input impedance on that measurement. You don't run into that real often, but it can be a variation, and that's probably going to be why there's going to be a variation in the different meters. Digital multimeters. I'm with you though. The VTVMs were an insta voltmeter, especially for that. They had very high input impedance.
Thank you.
Marconi and I like analog. When you tune a circuit, okay, in the old days when you had to actually tune the circuits, trying to do it on a digital, it can be done. I've done it. But it is much easier to watch a needle swing.
The peak or dip, the
to peak or dip the circuit.
So this one has a little bar that you can watch. Pretty fancy for 1982. All right. Anything else? Questions? Any questions? Or you guys want to get in here and poke at this stuff?
Okay.
They want to poke at it.
Then
All right. Have at it.